Okay, let's move on to the second talk of the conference. And now we have Alex McDonough from UC Davis, and he will tell us about the rotor-routing structures on plane graphs. Please.
Right. Thank you very much. Thanks everyone for being here. So this is, the title might look a little scary, but I'm going to have some animations that are going to help out, and I think it's a really cool topic, so I hope you enjoy it as well. This is all joint work with Ankan Ganguly. We were living together in Providence back when I was at Brown, and I told him that he's a probabilist. And I told him I had a project that would kind of combine his probability with my chip firing interests. And it turns out I was completely wrong. There's absolutely no probability in this project, but it was still incredibly fun. It was great working with him. So I have some animations to go along with some of this that I'll be flipping back and forth to. And you can find these slides on my webpage if you're interested. So the first thing I want to talk about is I want to define ribbon graphs. So there's some different perspectives for how people look at these, but what I really want to think of them as is just a graph where the edges around every vertex are given some sort of cyclic ordering. And we're going to just always use a clockwise ordering for this talk. So we can think of this as really a drawing of the graph on a particular plane, or you could do it on a higher dimensional surface, or a higher genus surface, I should say, not higher dimensional. So a plane graph is a ribbon graph with no edge crossings. This is like a specific embedding of a planar graph. So I have a couple examples up here of ribbon graphs. The first two are the same graph, but the first one is not a plane graph because you can see that there's a crossing here. You could not draw this on a sphere without some sort of intersection with this specific choice of ordering of the edges around each vertex. The second example is a plane graph because now we've drawn it so that the edge goes around this other vertex. And the third graph is a non-planar graph. So there's no way to get a plane graph from a non-planar graph. So this is another thing that can happen in certain situations. But this is just going to be graphs with a little bit of extra structure, which is going to be necessary for some of the things I define. And now we have this algorithm that I'm not going to give you enough time to read. This is going to be something that we're going to be working with throughout this talk, and we're going to be adjusting this definition over time. But let's look at an animation to see how this works. So we're going to start with a graph, and we have a spanning tree, which is the solid line. And we're going to choose, there's some vertex that's the sink and some vertex that's the chip. And the first step of the algorithm is that we're going to direct all of the edges towards the sink. And we're calling these rotors. So you'll notice that every vertex other than the sink has one rotor coming out of it. And the way this algorithm works is we're going to rotate the rotor where the chip is, and then we're going to move the chip across the rotor to the other side. We're always rotating it one position in this cyclic order. We're working with a ribbon graph, and we can speed it up a little bit and watch the chip move all around this graph, moving around these rotors until we finally stop when it reaches the sink. And now that we've reached the sink, we erase all of the directions on these edges, and we say that rotor routing has gone from that starting spanning tree to this other one. Rotor routing specifically with this choice of sink vertex and this choice of chip. So this is the basic single chip rotor routing algorithm that we're going to be working with. So some facts about rotor routing. So this was originally called the Eulerian-Walker's model. And the perspective was a little bit different, but some results that are implied is, first of all, the final output is always a spanning tree. Even though in the middle of the algorithm, you don't have spanning trees necessarily, as you saw, you're always going to end with a spanning tree. And that's something that you can play around with a little bit to see why it's true. It's not immediately obvious, but once you look at it the right way, it is a very simple argument why that's true. And then another lemma that comes up pretty quickly is that if we do this multiple times, if there's multiple chips, then it doesn't matter what order we move the rotors where the chips are. We can go in whatever order we want. And this brings us to our second clip of the day. Just giving you an example of having the chips moving in different orders and seeing that the same thing happens. So in this case, we have 2 chips. I have some numbers on here, which will make more sense in the future. And I have 3 different ways of resolving this. On the first one in the upper right, I have 1 chip going first. Bottom left, I have the other chip. And then the bottom right, I have the chips just taking turns. And in the middle of this, it doesn't necessarily look like they're all behaving the same way. But if you wait for it to finish, you're going to end up with the same spanning tree no matter what happens. And this is not an extremely difficult thing to show, but it ends up being very important for a lot of this idea. And I also want to mention this paper, Chip Firing and Rotor-Routing on Directed Graphs, by many big names in the field. This is the first paper that I read of like real research math papers, and it's a good one to start out with. It's very clear and is the one that really, for me at least, it puts these things in the perspective that I wanted to work with compared to some of the earlier ones had similar results, but a different perspective on it. So now we can adjust our algorithm with our observation from that last animation that we can have more than 1 chip. So, and then we just choose which chip we want to move at each time. We saw that this is well defined. It doesn't matter what order we do it in. And so here's our new slightly stronger algorithm than what we had last time. So next, what I want to do is introduce the Sandpile group, and I'm not going to read all this. I'm going to show an animation that doesn't even use all the same terminology and perspective, but it's the way I like to think of this. So a degree 0 divisor of the graph is an assignment of an integer to every vertex such that they sum to 0. This terminology comes from algebraic geometry. And these are going to form a group under pointwise addition. So if we add 2 of these, add the thing at each point, sums to 0, the final result is also going to sum to 0. And to get the Sandpile group, we're going to introduce this equivalence relation given by firing. And that's just some firing happen right there. So what you do to fire a vertex is it gives 1 chip to each of its neighbors. So every time you see these chips moving away from the vertex, that is 1 firing move, and it adjusts you from the starting position to the final position. And in certain circumstances, it makes sense to only allow firing in certain situations, like maybe you don't want to go negative. The way I like to set it up is you can fire anything whenever you feel like it, even if it's already negative, or you go into negative from being positive. And when you do that, a lot of the algebraic results become simpler. And you can also, this sort of gives another perspective for how you could define this thing. And a very important theorem that is central to all of the things that I do involving the Sandpile group and chip firing is that the size of the Sandpile group is the number of spanning trees of your graph. And we're going to see this come up very soon. So now we're going to give a new version of this rotor-routing algorithm where the input, instead of being a collection of chips, is an element of the Sandpile group. And I haven't proven yet that this is well defined. We'll see that in the next slide. So our input now is we take an element of the Sandpile group, and then we're going to choose some representative of that equivalence class that has non-negatively many chips away from the sync vertex. And we can always do that. You just kind of fire the sync vertex a whole bunch of times and then fire some other stuff. It's one of those things that if you play around with it a little bit, you should see that this is always possible. The thing that's definitely less obvious is that it doesn't matter which representative you choose. But that's what we're going to see in this next slide, which gives us another animation to look at. So this is a pretty short animation. You see we have the same situation. On the right, we're going to move the chip 3 times from this position. And what we end up with is we have all of our rotors are in the exact same position. And it looks like we just fired this bottom right vertex. So this is certainly not a proof by any means, but this should help give you an idea that chip firing is like doing a partial firing. So if you have things that are firing equivalent, they're also going to have the same effect when you do chip firing. And chip firing, when I say it, it's sort of synonymous with the sandpile group. When you think about it as like firing chips around on your graph. So this is well defined. This is that paper I was talking about earlier, Holroyd and many others. But there's also this fantastic fact that for any pair of spanning trees, there's exactly one element of the sandpile group that maps from the first tree to the other tree. So this tells us that rotor-routing is defining a free transitive action of the sandpile group on the set of spanning trees. And this for free transitive actions, if you're not as familiar with them, it's very similar to a bijection, but we have a group and we have a set. So the sandpile group always has an identity element, but the set of spanning trees doesn't always have a special spanning tree. So a free transitive action says that if you tell me which spanning tree to associate with the identity element of the sandpile group, then we get a bijection. And this is something that's good to look for if you ever have a group and a set that are the same size. So this led to a question on Math Overflow by Ellenberg, who asked, when is the rotor-routing action preserved after changing the sink vertex? So if we chose a different sink, how would that adjust this rotor-routing action? And it turns out there's a wonderful answer to this, proven by Chan, Church, and Grachow, which is that this rotor-routing action is preserved regardless of the sink vertex, if and only if G is a plane graph. So this is where it's important to work with plane graphs and not just ribbon graphs. And let's see this in action. So if we change the sink, we could, for example, fire this vertex in the lower left and then allow it to resolve in either case, allow these rotors to spin around. And as with before, it's not at all clear what's going to happen in the intermediate stages, but once you let it fully evaluate, you end up with the exact same spanning tree. And this is far from a proof, but hopefully this gives you some motivation for why this is true. So any questions so far? Yep.
How do you define the chip firing algorithm when there's a negative number of chips at a rotor?
Yeah, that's a good question. So there's two different perspectives. There's the rotor routing perspective and the chip firing. So the way that I do it with rotor routing is I just make sure that all the negatives are on the sink vertex, so I never have to worry about them. So that means that we have a perfectly, I mean, it's not immediately clear that it's well defined, but that's why I show that other animation. But we have this way of dealing with the case is we just take something that's equivalent as an element of the sandpile group, but has all of the negative chips on this one sink vertex. As far as the sandpile group, then there's no problem with firing negative things. It can just send a chip over and it's still in debt. Now it's in more debt, but yeah, that's how it is sometimes. Any more questions? Yep.
Start with a chip. You'll be able to reach at the sink by doing this rotor-routing.
Yeah, that's one of these questions that is, if you play around with it a little bit, it should make more sense. Sort of like you can't really get a situation where you go around forever and never return. There's this perspective involving unicycles that makes all of these things a lot more natural, where you add an extra edge from the starting place of the chip to the sink. And with that perspective, a lot of these ideas come down. So if you look at that paper by HLMPPW, you can get this unicycle perspective, and a lot of these results will follow pretty simply from that. In the interest of time, I think I'm going to continue, and then I'll take more questions later. But thank you for the questions. So we saw this clip 5. So now we have our final version of the rotor-routing algorithm, where the adjustment now is we have to input a plane graph. And the first step of the algorithm is to choose a sync vertex and just choose whatever we want instead of having that be part of the requirement for the input. And so now what we have is it really is a action of the sandpile group on the spanning trees. We need a plane, we need some specific like ribbon structure on our graph. And in particular, it's a plane graph, not just a normal graph. We don't need to pick a sync, which is nice. And I have some notation at the bottom. Don't worry about it. That's just so I can write things precisely in the slides. So now we had to do some definitions. There's this idea of sandpile torsors, which is was first stated in that math overflow question, but hasn't actually been defined anywhere. People talk about sandpile torsors, but there's not really a precise definition. So what we ended up going with is we say sandpile torsor action on a plane graph is some free transitive action of the sandpile group on the spanning tree. So it could be rotor-routing, it could be something else. And then we separate this out from a sandpile torsor algorithm, which is an algorithm that assigns a sandpile torsor action to every plane graph. So we saw that rotor-routing is a sandpile torsor algorithm because no matter what plane graph you give me, I can give you this sandpile torsor action, this free transitive action of the sandpile group on the set of spanning trees. And then the question is, so this is pretty natural to state, but it doesn't seem like there's definitely not some other way of doing this. So are there other natural algorithms that we might come up with? So in 2012, Baker and Wang used the Bernardi process to define another sandpile torsor algorithm. And I'm not going to tell you what goes into this, but it looks very different. It uses break divisors, and it has the same idea where you can define it on ribbon graphs where you need a sync, but then the sync doesn't matter if and only if you're on a plane graph. And this is something that they showed. And in general, on ribbon graphs, the Bernardi process looks different than the rotor-routing. You're going to get a different result, even if you choose the same choice of sync vertex. But the really fascinating thing that they showed is that the rotor-routing algorithm and Bernardi algorithm are actually equivalent when we restrict to plane graphs. So that's a little bit surprising. And there's a couple other descriptions. Oh, yep. Oh, yeah. So what equivalent means is you get the exact. So the question was, what does equivalent mean? And the answer is that you get the exact same sandpile torsor action. So if you take the same element of the sandpile group and the same element of the set of spanning trees, it'll give you the same final result. Yeah, thank you. So there's some other descriptions in this case. These other ones are just sort of other perspectives of describing the Bernardi algorithm on plane graphs, or in the second case, it's talking about this Trinity perspective. And in these cases, there's not another perspective that works with ribbon graphs that have a sync, but you get this same case where these end up being identical. So we keep finding the same thing when we kind of take different paths to look, which is surprising. And this leads to the conjecture by Klivans in her book. For plane graphs, there's only one sandpile torsor structure. And I know what a lot of people are probably wondering, what does this mean? That's part of the conjecture. Try to figure out what this means and then prove it. Because that's one of the most challenging parts, is to figure out what it means to have like a specific sandpile torsor structure, because you can certainly just choose whatever free transitive action you want on each graph and have them be completely unrelated, but that doesn't really feel meaningful. So we're looking for some kind of natural action, but we're afraid to use the word natural because then all the category theorists will get mad at us and tell us that's not really what's going on. So That's the first goal, is to figure out what this should even mean. So first of all, there's actually 4 different Sandpile Torsor algorithms that you get from Rotor-Routing, because you can just reverse the direction of everything and go counterclockwise instead of clockwise. You can also take the inverse. So you basically treat the sinks as sources and the sources as sinks, or the chips and versus sources, same idea. And this will happen for any Sandpile Torsor algorithm. You actually get these 4 possibilities. So we said that these have the same structure. So 2 Sandpile Torsor algorithms have the same structure if you can get from one to the other by these, if it's one of these 4 things got by these 2 Z2 actions. And we're still not done. This is kind of nice to have this, but we're so far from having an actual definition of some sort of consistency for how a Sandpile Torsor is allowed to react or act. I don't know why I said react. React to the graph that it is given. You could have clockwise rotor-routing on some graphs, counterclockwise on other ones. You could have clockwise on some, and some weird thing that doesn't make sense on some specific graph. And the first thing that I came up with when I was first looking at this project, when I was starting in grad school, is to have some sort of automorphism invariance. Like if you have an automorphism of your plane graph, it should still act the same way. And this is good to require. It doesn't get you very far, because there's a lot of graphs that don't have any non-trivial automorphisms, and we still want some way to discuss how the action on one plane graph is related to another one. So this is where I was stumped for many years of trying to figure out some sort of definition of consistency. And we found it. So this is another one that is easier through animation. So what we ended up finding that was true about rotor-routing that we in turn made as our definition of consistency is, first of all, so we saw before that this is what happens by rotor-routing. We get from the thing on the left to the thing on the right. We're going to choose an edge that's in both of these, and we're going to contract it. And then we're going to see what happens when we do rotor-routing. And it's very important here that the chip and the sink are next to each other, and there's just one chip. Because we can't actually have this action be of the Sandpile group, because then it's not well defined what happens after you contract E. If you contract an edge, suddenly the Sandpile group changes what is going on. So this was very difficult to come up with, but it turns out that this is always going to happen as we get this this commuting diagram in this specific instance where we have this edge that is in both the starting spanning tree and the final one. And some people might be able to guess what's going to happen next is we get sort of the dual picture with deletions. So if we choose an edge that's not in the starting spanning tree or the final spanning tree and we delete it, then what we end up getting is the same final spanning tree, but the graph has now deleted this edge. So I spoiled that a little bit, but hopefully you don't mind. And I chose the sort of simplest non-trivial example where you actually get some interesting stuff going on, where it's not just like, it is easy to show if you don't cross that edge. When you do, it's a little bit trickier to say what happens. And in the interest in time, I think I'm going to skip the last thing. This is just something that tells us we don't really have to worry about cut vertices. It ends up, we're not even positive that it's not implied by the other 2, but it ended up being really helpful for us to have this extra thing. So you can look at that on your own if you want to. This ended up taking us 3 cases for each of the first 2. It was tricky, but coming up with this, coming up with a conjecture of this being true was more challenging than proving it itself. It's sort of a medium difficulty type of thing. So we use this definition or this property to define what it would mean to be a consistent Sandpile Torsor algorithm. So a Sandpile Torsor algorithm is consistent if it satisfies these properties of like you have this contraction commuting with contraction in this specific case, commuting with deletion in this specific case, and then something about cut vertices that basically goes down and we only have, let's just focus on 2 connected graphs is kind of the idea. 1 minute, okay, I can get through this pretty quick. So here's the big theorem, is in fact, this is a defining property of rotor routing. It's not just a property of rotor routing. Every consistent Sandpile Torsor algorithm is gonna have the same structure. And so to actually prove this was very challenging. This is probably of any proof I've been involved in, this is the one I'm most proud of. It started, we had to find a way of describing rotor routing in general by sort of local moves that would fully describe things. Then we use induction to reduce to 4 special cases. And then it's a nightmare to resolve those 4 special cases. That ended up being a lot of work on its own. And the last thing I'm not going to get into is I think that the right generalization is to regular matroids. And I can make all the statements in regular matroid land. I'm just still working on proving these. And we basically have the same conjecture of this putting things in regular matroid land, this algorithm that's known, is it consistent and is it the unique consistent one? I think I pretty much have a proof of the first part, but the second one could be challenging because it was very challenging in the graph case. And that's it. Thank you for listening. Here's a crazy graph that we had to use for one of our cases.
Do we have any more questions for Alex?
Just before the Sandpile matrix tree theorem, I noticed the definition of Laplacian matrix. I'm wondering, what is the significance of the matrix there just before the matrix tree theorem?
Yeah, that's a good question. That's something that I definitely sped way too quickly through because I wanted to give sort of the easiest to define definition of the Sandpile group. But the idea is this Laplacian matrix has the stuff on the diagonal is the degree of your vertex, and then the stuff on the off diagonal is -1 if there's a connection between the 2 vertices and 0 otherwise. So what you can realize is that doing a firing move is exactly adding some row of this Laplacian matrix. In particular, you add the row associated with V, or actually you should really subtract the row associated with V, because then you subtract degree many chips from that vertex and you add it to the other one. So there's a way of describing this purely algebraically, but I kind of like the dynamical perspective because it gives you a nice way to think about it.
Okay, thank you. More questions?
In the deletion condition, if the edge that you delete is actually in the final spanning tree, what happens then? Because you can't.
So you're not allowed to do that. We're always contracting edges that are in the spanning tree or deleting edges that are not in the spanning tree. So there's a lot of restrictions to what we are actually, the situation where we could actually get this sort of consistency. So it was really exciting when we found that it was enough to be a defining property for rotor routing. But yeah, you only delete the stuff not in the tree, you contract the stuff that is in the tree.
So more questions? So you mentioned at the end this case analysis. That seems that's very tedious. Do you think there's a way of getting rid of this case analysis?
I'm scared to make too much of a guess, but I think that if there was, it would have to be coming from like a higher up perspective. Like maybe there's some deep theorem in Matroid theory that you could use to do this. But I think without kind of going higher up and looking from there, I think that it really is necessary. And some of the cases, I mean, there's no way to completely get rid of them because there's situations where clockwise rotor routing looks the same as counterclockwise rotor routing. So you got to figure out exactly when they differentiate from each other. So I really do feel like we found a reasonable proof of this thing. I'm not super disappointed in an ending in case analysis. I think that is kind of the way it had to go.
Okay, thank you. Let's thank Alex again for a very interesting talk.
Thank you, everyone.